Hi, I'd like to show you the solutions to this problem 94 in the course MATH3411, and it's about an encryption scheme where we take a message like this. So M here is the message consisting of some letters M1, M2, M3, M4 and so forth. And the way that we encrypt these messages or encipher these messages to a ciphertext like this is as follows. We take the letters of the message, we turn them into some numbers given by this little table here. We write those numbers, which are confusingly also called M1 and 2 and so forth, but the first number is there, the second number is there, third and so forth in this little array or matrix. And then we take a 2 by 2 matrix A, multiply it onto the left hand side to get another 2 by something matrix, and then those numbers there we convert back to these letters here, and then we read off column by column to get this message there. So it's a slightly more complicated scheme than we have seen with transposition ciphers or those very, very classical ciphers, but it's not too hard to crack if we were Eves, the eavesdropper. But let's see how it works. So one thing I haven't mentioned yet is that all of these calculations are conducted mod 29. 29 seems strangely specific, oddly specific, but you see that this table here has in fact 29 characters in it, and 29 is a prime number, so modular arithmetic in 29 is pretty good. And one little comment too is that when we do translate letters into numbers, especially when we'll get to RSA coding, then it's good to avoid zeros and ones, because any powers of zeros and ones are, well, they're not going to be different from what we start with, so that leaves us open to attack by Eve. Not necessarily in this problem here, but in general it's good to start with A, B, etc. from something that's a little bit further away from 0 or 1 or even 2. Okay, what do we actually have to do? We have to, in the first part there, we have to decipher this ciphertext here, that love brew. Okay, so whatever that means, that's not the actual message, that's not the plaintext, that's the ciphertext, where we have to somehow get from the ciphertext back to the plaintext by deciphering it. And we're told that the matrix that's used to encipher this one, the message that it gets to be that ciphertext there, is this one here, 2378. So, how do we do that? Well, I suppose we have to go backwards. So let's have a look. If we call this matrix C, then we've got that C is equal to A times this matrix here, which we could call M. So we want to know the matrix M, because then we can find the message, the plaintext. So that's exactly what we want to do. So this matrix here, M, is equal to, well, I suppose it's the inverse of A times C. And well, what is the inverse of A? Well, we don't know yet. We'll have to find that out. But first of all, in order to have an inverse, this matrix has to be invertible. So that's implicitly part of the statement of the question as well. Okay, cool. Well, let's have a look. So this will be a 2 by 2 matrix, and then C there. Well, that's the matrix that we get from this love brew ciphertext. Sorry, I just deleted half of the. Oh no, we are missing half of the ciphertext, and we're back. And that's given by a little 2 by 3 matrix with a love brew like so, except that we have to replace these letters by the equivalent numbers down here. So for instance, the U's here, they are 23s. So if we have 23 there and 23 there, and then we've got the B there, that was somewhere here, that's equal to 4. So if we get rid of the B and just call it a 4, then we've done half of this translation. Now we just need L, V and R. L was 14, or is 14, could possibly say a little bit more accurately. And we've got V is somewhere over here, 24. And finally we've got R, which is, that was a flourishing 2 there, a little bit too flourishing in my opinion, but I'll let it be. Here we go, 20. Okay, so this is our matrix C with these numbers here. Okay, what else? We have the inverse of A that we have to find here. So we've got to find the inverse of this matrix here, mod 29. So how do we do that? Well, you could do it in several ways, but either row reduce or use a little formula. I think I might use the formula. So that you might have seen in high school or first year maths or whatever, where we look at the determinant. So this is the determinant 2 times 8 minus 7 times 3. And then we are going to look at the entries here on the diagonal. We swap them. And then we put a little minus in front of these, minus 7. And there we go. Technically speaking, since we're dealing with modular arithmetic, we don't really have fractions like this. So what I really should say is this, whatever it is, inverse. So that's just being a little bit more precise about it. Okay, so what now? Well, I suppose let's calculate what this is equal to. So 2 times 8 minus 7 times 3 is 16 minus 21, which is minus 5 inverse. And then we've got this matrix here again, 8, 2, minus 3, minus 7. And there we go. What is the inverse of minus 5? Well, we can just guess. We're talking modular arithmetic mod 29. So we've got to multiply this number by something to get 1, or in other words, for instance, 30. So we could say, what about minus 6? Ah, that actually works. That actually works. So minus 6 times minus 5 is 30, which is 1 mod 29. So this is minus 6. And here I should say in all of this is in Z29. And yep, here we go, 8 minus 3 minus 7, 2. And I'm soon going to run out of space here. I should hurry up and calculate it. So I have minus 6 times 8, that's minus 48. And then I've got minus minus 6 times 7, that's 42. And I've got minus minus 6 times 3, which is 18. And finally I have minus 12 there. And then I can tidy that 48 up a little bit by adding 2 lots of 29, for instance, so 58. So that's equal to 10. And then I've got 18. Yeah, I could reduce that a little bit if I wanted to minus something, about 11. But what about 42? That makes a bit more sense to reduce. So here we have 13. And I'll just leave the minus 12. Why not? And there I have the inverse of A. So if I write that up a little bit nice and tidy, then we can proceed with the multiplication over here. So here we have 10 and 18 and 13 and minus 12, and that should give us something. So here, I'll just copy this up here. Okay, well, what is that something? Well, here again, we just have to do matrix multiplication, 10 times 14 plus 18 times 23. And here, if we wanted to make things a little bit simpler for us, we could reduce a little bit. 23 is the same as minus 6, and 24 is the same as minus 5. And 20, let's call that minus 9. Okay, that's enough reducing. And that might simplify the calculations just a little bit if you're doing these things by hand, but yeah, up to you whether you want to do that or not. And yeah, and the matrix that you get out of it, we can just write up here. 3, 22, 22, 3, 13, and sorry. And 5 and 13. Here we go. 5 and 13. Okay. So what is the message? Well, I suppose that means that the message is equal to, well, the first letter is given by 3, so that's an A. The second letter is the 22 here, and that's given by, represents the T there. And then we have another 22 there, so we're reading column by column. And atta, and 5 is C. Oh, okay, so, and let's check. Yep, K is 13. Attack! So that seems a bit unexpectedly militant, but I suppose a lot of cryptography was generated for the purpose of keeping secrets during war, so maybe that's not completely out of context. But anyway, that is the solution. I'll make it militant by just getting rid of those exclamation marks. Attack. Oh, attack. Okay. The second part of this question is sort of cool. It's a little bit technical and with a bit of calculation, but I like it a lot. And it says something about the nature of cryptography more generally. So it says, using a secret matrix A, I sent the ciphertext, this stuff there. So I had some message and I was sending, enciphering it in the way that we've seen, and we get this ciphertext and so forth. Now, this is supposed to be a secret ciphertext. However, I was foolish. I started my message with hello, and if you're trying to crack this code here, you might know me and you might know that I said hello. So if you guessed that I said hello, then you can actually decipher this message. And in fact, that's what we have to do. Can you decipher the message? So why is this bit of information enough for us to crack the whole code? Well, let's have a look. So first of all, we need to find out what the matrix for this ciphertext is. And then we also can say something about the matrix here, the matrix M here, because we know a little bit of the message already. In particular, we know the first 5 letters of the message, and I suppose the 6th as well. There's a space there as well. But that means that we've got the numbers for H, E, L, L being there, H, E, L, L, and so forth and so on. We're going to use that information. Here I've written up the numbers that correspond to Z, B, X, and so forth. So Z, B, X, and so forth here. And over here, I've got the numbers that correspond to the message, the numbers that I want to try to find. And I know that the message starts with hello. So the first number that goes there is the one that corresponds to H, which is 10. And then we've got E, which is 7 there. And then we've got 2 L's, which are 14. And then we've got an O coming after that, which is 17. And we've got a space character and so forth. But let's just have a look at, actually might as well just have the space character there, and so forth and so on. So now we can use this bit of the message to figure out the rest. And how do we do that? Well, I suppose let's have a look at what happens when we do this matrix multiplication. We've got this little 2 by 2 matrix, which when you multiply it onto this matrix here, gives us, well, of course, C. But in particular, if we look at this part of the message matrix, this 10 and 14 and 7, maybe I should use a slightly different pen. Here we go, this there. Well, that multiplied by A on the left-hand side will exactly give us this little 2 by 2 matrix over there. I'm going to call this matrix M prime and this little matrix C prime. And then I can write, well, we've got C prime is equal to A times M prime. What I want to find out is the matrix M, and that's equal to the inverse of A times C. So if I can find the inverse of A somehow, then I can find C. And of course I can do that because the inverse of A is equal to, well, what I get if I look at the inverse over there. Here we go. Inverse A times C prime. That's equal to M prime. And if I then divide by the inverse of C prime, hoping that that will make sense, then I will get that we have the inverse of A here. So this is going to be equal to this little matrix M prime times the inverse of this little matrix there, C prime. Okay, so I can write this as M prime C prime, oh, there's a inverse missing, times C prime inverse, times the matrix that we have there, C, and there we're done, in principle. We first have to figure out, well, that one's easy, we know the message there, so that's equal to this 10, 14, 7, 14 little matrix, that was M prime. Now we've got to figure out what this matrix is, the inverse of that matrix there, and then we've got to multiply it all by this big matrix over there, which we've got here, and I won't draw it all up, but 28, 4, 26, 25, and so forth and so on, dot, 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 and there we go. So that's what we have to do. So there's a bit of work to do, but the first thing to do is to find the inverse of this little C matrix over there. And if we tidy that up a little bit, 28 is the same as -1, 26 is the same as -3, all of it mod 29. 4 is 4, -4 instead of 25. Okay, that's a little bit easier to deal with those numbers there. So what's the inverse of this matrix? Well, C dash inverse is equal to, I suppose, 1 over the determinant of this, or here we're dealing with modular arithmetic, so the inverse of that determinant, -1 times -4, -4 times -3, and the inverse of this number there. And then we have to multiply it onto the matrix that we get by swapping the diagonal entries, so -4 and -1, and then putting a minus in front of the counter diagonal entry, so -4 and 3. Okay, so let's have a look. We've got -1 times -4 is 4, and over here we have -3 times 4 is 12, 4 plus 12 is 16. The inverse of that is obviously 20. No, you'd have to figure that out. I have figured it out beforehand, and just that gives 20. There's a tiny little bit of calculation there, not much. And that's times this matrix here, -4, -4, 3, -1. And that gives you, once you tidy things up a little bit, this matrix here, 7, 7, 7, 7, 2, and 9. And there we go. So this matrix here is the one that we wanted to find in order to multiply it in the middle here. So 7, 7, 2, 9. And then we've got these matrices to multiply together here. I'm not going to go into the detail, but when we do multiply it in this way, then we get a matrix here, which I'll write up now. And here it is. So what is that message? Well, it says 10, 7, 14, 14, and so forth. Okay, yeah. But what does it actually mean in the original formulation in terms of letters that we had? Well, okay, we just have to figure out what these numbers are. We've got 10, which is H. So that's starting off well. But of course, we knew that was the case. We have hello to begin with. So here we go, hello. Might as well just cheat a little bit. Well, it's not really cheating, but that's these first 1, 2, 3, 4, 5 letters, and 7. That is an E. Hello E. Hello E. And then we've got 24 and 7. So 24 is V, and hello Eve. You're trying to break our code again. That's nice of us to say hello to Eve, but wait a second, then we've got 20, which is R. Oh, Eva, Eva, hello Eva. That sounds a bit, could it possibly be, 27 is Y. Hello every, could it be everyone or something? Let's see. Well, there are 4 letters left, so it's probably not quite 1, but I'm guessing that you can guess what it is now. So B is 4, so every... yep, and we have 17, 6 and 27. 7, O for B, 6 is D, everybody, and that's the 27. And yeah, hello everybody, hello. Much less militant than the first part, so that's nice and friendly, and that is indeed the solution to our part B. Now, there is a third part as well, part C. It's more of a speculative part, or a sort of a hand-wavy, talky part. And there's no real answer here, but it's more about figuring out, well, how good is this encryption scheme? So if we didn't know anything about the message like we did here, but just used brute force to test. Okay, so here we have some ciphertext, like for instance this stuff there, and we just tested all the matrices A that we could think of. Well, how difficult would it be then to figure out what the ciphertext was? And I suppose that really depends on how long the message is. If the message is just 4 letters, so you just have a very small, or even 2 letters, say, then, well, you might find very many different matrices A for which the ciphertext would give something meaningful. For instance, if we said, 2, TO as the message, well, maybe over there we'd maybe get, depending on A there, we could get all sorts of messages like BE or AS, like as, or a whole lot of 2-letter messages. So we wouldn't know which of those messages were the right one, because we've got so many of them, so many meaningful deciphers. On the other hand, if our messages are a little bit longer, even to the point where we just have 3 or something, 3 columns here, maybe 6 letters, I reckon then it would be relatively, well, it wouldn't, it will sometimes happen that you could take those letters there and find some matrix that, or rather the other way, sorry, that if we get to ciphertext with 6 letters there, then you could find some matrix here that when you apply it to decipher to get some message there, it's not just random letters, it might actually be something meaningful. But I think if we go any further than that, and that's a very short message, but if we go maybe to 8, then it's rather unlikely. If we go to 20, it's impossible. Like, you're not going to take some ciphertext and just throw some random 2x2 matrix at it and get something meaningful if there are like 10 columns here or 20 letters all in all. And I suppose one way of measuring that, well, you can do that a lot better than what I'm going to say now, but one rough, naive way of measuring it is, well, how many matrices do we have? A there. And I suppose we have 29 to the power of 4, and that's a decent number of them, but it's not a massive number of them. Definitely not compared to how many messages we can write if we are allowed to have 10 letters, for instance. But also even more, these have to be non-singular, invertible in other words, so that reduces the number of these A's dramatically, and or in other words, the number of these keys dramatically. So yeah, we just don't have a lot of keys, so therefore this crypto system here is pretty easy to break. You don't need long messages, or in other words, long ciphertexts to be able to guess the key that will give you a unique, or relatively unique, meaningful full message. And that's what part C was asking us to discuss, and I have just discussed it. And you can discuss it too if you feel that you disagree with this, with my verdict on that matter, and please go forth and think about it yourself. And please do feel free to disagree if you can see some details that I have not. This is a bit of a discussion slash thinking type of problem, that part C that I haven't written up there. Anyway, is there more to say about this? Not really, except that I hope that it mainly made sense, wasn't too fiddly and technical, and that you now understand this. And yeah, Thank you very much.